Hi, this is Mr. McLean. In this video, we'll be taking a look at section 3.3. And in this area, we're going to be focusing in on the idea of acid-base chemistry. We'll also talk about the pH scale and how buffers play a major role in both organisms and in ecosystems. So this idea of acid-base chemistry is really pretty significant when we start taking a look at the study of biology. We know that there are major concerns with maintaining that homeostatic level in terms of the acidity or basic nature of different biological solutions. So we want to start off here by taking a look at a scenario, and I'm going to come back to the slide here in a minute, but in this scenario right here, what we're doing is we're taking a look at a quantity of water. Okay, and if you think about, in order for the water dissociation equation to work out, we're going to end up with initially two full molecules of water over here. Okay, so we have a hydrogen bond between these hydrogen-oxygen setup. So we have two water molecules. And the depiction of this arrow, which is yielding to the left and the right, means that it can kind of move in either direction. The direction of the reaction could be breaking this down, or it could be re-establishing it back into water. So at any point in time, occasionally one of the water molecules will successfully extract the hydrogen off of a nearby water molecule. So in this case right here, the oxygen pulls harder than this one did, and what it'll do is it'll give us a hydronium ion. So whenever you have H3O and positive, so we have a positive charge to this, this is called hydronium ion. And when we look at hydroxide, that's the other one that's going to be remaining in that situation, and that's the ion that exists that was missing the hydrogen. So if we take these two things and we put them back together, we're going to end up once again with two water molecules. So if we look at the equation as far as how it's written out, we have four hydrogens. And if I go over here and I count it up, I see 1, 2, 3, 4. And we go over here and we have two oxygens and we have two oxygens. So that's the balanced equation for every two water molecules that can dissociate into hydronium and hydroxide ion. And at this point right now, we have a balance between these two ions. So therefore, we're looking at something that would technically be classified as being neutral. And whenever that's the case with these ions, they are in dynamic equilibrium. So they are balanced off, and even if the reaction goes this way, it'll go right back that way because these two are balanced with each other. So as we go through here and we revisit that first slide, it says hydrogen atom leaves its electron behind and is transferred as a proton or as a hydrogen ion. So a hydrogen ion is a proton, and that's why we end up ending up with a positive charge associated with it. The molecule with the extra proton is now going to be H3O plus, known as hydronium. And what we find, so if we go over here, let me open up a whiteboard for us, and let me move ahead over to another area of the whiteboard. So over here, we were talking about if I have a water molecule, okay, and I have another water molecule, and they're bonded together. Okay, so basically I have my two H2Os, all right, and then we go through this reaction, and this one here is taking the extra hydrogen, and this one over here is taking, or is missing that hydrogen. This is what we were looking at. This molecule right here, what will end up happening in many cases is we will see a hydrogen coming off of this. Okay, so when we look at acids, when we think about, measure of something as being acidic or what have you, we're talking a lot of times with the measure of how much hydrogen is in that system, how much free and extra hydrogen is in there. So when you end up with H3O, that's going to have the capacity to release some of those extra hydrogens into the solution. So that becomes really critical when we start moving into some of the other processes throughout biology that we're going to study. Okay, so it tells us here why this works out mathematically, and even though it's rare, it says dissociation has a great effect. So it's not like all these molecules are doing this. It's rare, but it's still yet significant, and it's saying that ratio of hydrogen and hydroxide will ultimately impact chemistry of a cell. So if that H3O forms the water and then releases hydrogen, that would make this hydrogen level go up, which is associated with a more acidic environment, and likewise, this value would go down in relative position. So in pure water, your concentration of hydrogen ion and hydroxide ion are going to be equal. Okay? So it says if you add things like an acid, that's going to disproportionately change that solution. If you add a base, it's going to bump this value up. If you add an acid, it's going to bump this value up. So wherever you're at, if you start with pure water or something that has a pH similar to pure water, you're going to have these two in equilibrium. Okay? So by definition, an acid is any substance that can increase the hydrogen ion concentration of a solution. So when we go through and we start looking at functional groups in chapter 4, some of our functional groups will kick off hydrogen ions, which indicates that they have acidic properties. Anything that is classified as a base is going to reduce the hydrogen ion concentration. A lot of times for the bases, you see the OH minus, the hydroxide, because hydroxide will grab this hydrogen. So if I click back over to my sheet here and we slide up here a little bit, if you have a hydrogen, let's say a hydroxide like this, that hydroxide is going to try to grab, losing my pen here, it's going to try to grab some of the hydrogen that would be in the solution and reestablish that as H2O. And if you think about it, this is a base. This is found in an acid. If these two are in the same proportion, then you're going to get something neutral, and water would be the model of being neutral in that particular case. So the acid-base chemistry is definitely something we need to be concerned with. Now, the math behind this. So when we're talking about the number of hydronium ions or hydroxide ions, and we're talking about things that are extremely, extremely small over a large quantity of substance there. So what they did is they used this representation in terms of the logarithmic scale. So the scale to represent our concentrations of these different ions is called the pH scale. And it says in an aqueous solution at 25 degrees Celsius, the product of the hydrogen and the hydroxide is constant, and it can be written as product of hydrogen, product of hydroxide is equal to 10 to the negative 14th. So the pH of a solution is what we refer to as the negative log of the hydrogen ion concentration. Now, that might sound more complex than what we need to really get into in this class here. What you need to be able to do is to be able to look at something and be able to understand how those two relationships exist, okay? And because it's a negative log, so let's take a look at this here. We recognize that on the pH scale, 7 is the neutral component. 7 is right in the middle. So if I had something where my hydrogen ion concentration was 10 to the negative 7th, okay? What that is, that's right in the middle, Okay, so we'd have the same amount of hydrogen ion, we'd have the same amount of hydronium ion, so that would be neutral. And when we go in here, the negative log of the concentration of hydrogen ion. So what that does is it's basically going to say that the negative of the 10 to the negative 7th, and then obviously with the log scale, it's going to give us my pH as being 7. So whenever we're dealing with this, that means that this is the concentration of hydrogen, and in my hydronium ion, or my hydroxide ion, would also be the same, because the product of those two together would give me 10 to the negative 14th. Okay, so let's take a look at something else. Let's try a different one, and let me click over here. So since we know that our pH scale, if we take a look at this, as we go through here, if I said that, and these are 10 to the negative 7th, so if I am working in this case here, and we say, all right, here's my pH of 7, here's my pH of 6, 5, 4, 3, 2, 1, and then over here in the positive 8, 9, 10, 11, all the way down to 14. This actually can go all the way up to 0. Okay, so if I jump in here and I say, all right, at this point I have a hydrogen ion concentration that's going to be 10 to the negative 7th. Okay? If I go this direction, I become more acidic. So a pH of 6 is going to give me 10 to the negative 6. So that's actually going to say that I have a 10-fold increase. I have 10 times more hydrogen ion whenever I go from a 7 to a 6. If I were to go through here and I look at this one here, this one is going to be 10 to the negative 5. So it's 10 times greater than 6, but it's 100 times greater than 7. So being that this is a log scale, each one of these steps, if we jump, let's say I want to jump all the way to 4, okay? So if I'm jumping to 4, this is 10. From 7 to 6 is 10. 6 to 5 is 10. 5 to 4 is 10. So I have 1,000. So a pH of 4 is 1,000 times greater hydrogen ion concentration than a pH of 7. All right, let's go on the basic side of things. If I have a pH of 8, all right, so a pH of 8, what that tells me is that in this particular situation, I have a concentration of hydrogen ion. Hydrogen ion is going to be equal to 10 to the negative 8th. So my hydroxide ion, in this case, would be 10 to the negative 6th. So the sum of those things will give me my 10 to the negative 14th. Okay? So as we move into the more basic range, what we're going to find is that even though this number increases in terms of the hydrogen ion concentration, it's actually getting smaller because that's a power of 10 and it's a negative. So let's look at one more. If I were to grab pH of 10, let's say pH 10. So for my hydrogen ion concentration, slide this up here a little bit. All right, so my hydrogen ion concentration is equal to 10 to the negative 10th. My hydroxide ion is going to be 10 to the negative 4th. So the total still has to be 10 to the negative 14th. So what does that mean? When I go down here and I'm looking at something that has a pH of 7 versus a pH of 10, well, that would be, let me change my pen color, that'd be 10 times, 100 times, it's 1,000 times more acidic or more basic. So for every step on the pH scale, you're going to get an incremental change that's going to be equivalent to a 10-fold change. Okay? So as we take a look at this and wrap this up, the last point that we want to make is that we can't have these massive fluctuations in pH within living organisms. pH should be pretty close to 7. We'll talk about some specifics in class, but there are absolutely critical needs for buffers. And a buffer is something that minimizes the changes of these concentrations. And they are typically what's called a conjugate acid-base pair. So it'll reversibly, provide hydrogens or help remove the hydrogens out of the system. So, for example, in our blood, if we're trying to maintain a blood pH without too much fluctuation, there are critical buffers that are going to serve that role. If you're taking a look at a situation like a body of water, the idea is that every time we got pollution or rain, pH could potentially change. So for maintaining homeostasis and maintaining a safe environment internally, a buffer is something that's going to be very critical. So as we kind of finish this off, like I said, the final point that we want to mention is that 7 is neutral. Less than 7 pushes us towards the acidic range. Every number you see on here is a representation of the negative log of the hydrogen ion concentration. So if I go to number 12, if I'm looking at pH 12, what that's telling me is hydrogen is 10 to the negative 12, and therefore the hydroxide is 10 to the negative 2, because the sum of those two will give me 10 to the 14th, or negative 14th. Hopefully that helps, and we'll take a look at more things in Chapter 4.